Bismillah ar-Rahman ar-Rahim. So today we'll start a lecture of water quality modeling, feed-forward system. First of all, here we will check how is the downstream water body affected by the process in the system upstream. So remember, if you have like lakes, and these lakes are going from, this is going to be the water from this lake going to this lake, and the water of this lake going to another lake, and this is the input of the first lake. So this is lake number 1, and this is lake number 2. So what we're checking is, this is downstream, and this is upstream. So we want to check what is the effect downstream on this lake by the process in the lake upstream. So this lake will affect this lake. And also we will check also in this the dynamics in the upstream that control what I see in my area of interest. Let's say my area of interest is this lake number 2. Sometimes it's lake number 3, 4, or lake number 10. Let's look at the simplest case, which is a 2 lake in series, and see how it's going to be affected. Let's say that if you have lake number 1, which is going to be considered either lake or CSTR, they all mean the same thing. Lake number 1 has volume, and it has concentration. Same thing, this lake number 1 has a loading, and let's just call this loading 1. And of course there is some degradation, decay, Q1. And then the flow rate leaving lake number 1 toward lake number 2, and these are the simplest we have. We could call this one the flow rate going from lake 1 to lake 2. So this is 1, 2. This is flow rate 1, 2. And this is, of course, this here, there is K2, and this is the degradation factor of lake number 2. And of course, I'm going to assume that there is also loading for lake 2. And the flow rate, of course, the flow rate leaving lake 2, it's called Q2 to 3, to a lake number 3 later on. And of course, this lake 2 has volume, and it has concentration that is happening inside the lake number 2. Let's look at the equation that govern this. Okay, so whatever governing this is, once you do a mass balance, that for lake number 1, this is lake number 1, V1 dC1 over dt is equal load of lake number 1, this is the input, minus whatever happening in lake number 1, K1, V1, C1, and whatever leaving lake number 1, Q12 times C1. These are both output, and this is input. Okay. So now we will do for lake number 2. Lake number 2. V2 dC2 over dt, the input of lake 2, W2, plus whatever, remember this, leaving lake 1, going to lake 2. This is still an input for lake 2. Remember here? This is whatever's entering here, Q12 times the concentration C1. That's going to be the input to lake 2. It's an output of lake 2. It's going to be an input for an output of lake 1. It's going to be an input for lake 2. So this is going to be, this both going to be an input. And of course, leaving the loading of lake 2, Q23, times C2 and plus the decay of lake number 2 K2 V2 C2. This is both are the output. Okay, so now we could figure out that the feed forward, that the downstream concentration C2 is it's really influenced by the upstream concentration C1. So C2 is really directly related to C1. This means that any change in the first lake, like if you have more loading, if you have more removal, if you have decay, if you have flushing, if you have dilution, this will propagate to the second lake, will affect it either positively or negatively. The feed-forward principle that downstream concentration C depends on the upstream loading. All the loading that affect the upstream will affect the concentration C downstream. Okay, so let's look at the cascade model at steady state. If you have let's say we have 4 reactors, or we have 4 lakes. And these 4 lakes are, let me just put 4 lakes here first. Okay, and you have, let's say this is lake 1, lake 2, lake 3, lake 4. If you have Q, let's say 0, 1, original to going to lake 1, and you'll have degradation K1, and here the flow rate is Q1 to lake 1 to lake 2, and of course you'll have K2, and then you'll have Q2 3, and then you'll have K3, and then the flow rate from number 3 to number 4, and of course there's the decay in the 4th lake. And of course the effluent leaving lake number 4 is Q4, and let's just call it 5, just leaving to another lake number 5, and then 5 to 6, whatever is the distribution of these flows. And let's assume that Q1 is equal to Q2 is equal to Q3 equal to Q4. And let's also assume that Q01 equal to Q12 equal to Q23, Q34, and Q45. And let's also assume that volume 1 equal to volume 2 equal to volume 3 equal to volume 4. Okay, so we'll have all these assumptions that all the K's are constant, equal to each other, and the flow rate are all the same, and the volume are all the same. So once we do V1 for the first reactor, V1 dC1 over dt, and that's going to give you automatic 0 because you're talking about steady state now. Okay, so dC1 over dt is always 0, and dC2 over dt is equal to 0 because you're talking about hundreds and thousands of years of operation. And that's going to give you equal, if you look at the lake number 1, that's going to be going Q01 concentration 0 minus Q12 C1 minus K1 V1 C1. So it is, that's from lake number 1, V1 dC1 over dt, loading, and of course that's also if there is any loading coming up, so it's going to be a loading 1 minus, let's see if you wanna find, let's look at C1 here. If you want to do C1 and take C1 as a common factor, that's going to give you Q01 C0 over Q12 plus K1 volume 1. And that's what I need to show you, that it is Q01, and since they're all similar, over Q12 plus K1 V1 C0. Okay, so Q over Q plus KV is the factor that we need to put all the time like that. So this is what we have to do for lake number 1, that the concentration C1 is equal Q over Q plus KV. And I'm assuming that K1 is equal to all the lakes, and the flow rate is equal to all the lakes. So it's going to be like this C1. And then if you do for lake number 2, you will get the same thing. You will get the same thing. You will get that C2 leaving lake 2 is equal C1 leaving lake 1, Q over Q plus KV. And if you do the same thing for combining lake 1 and lake 2, you will end up with C2 leaving lake number 2 as a function of the original C0. This is going to give you Q over Q plus KV times Q over Q plus KV, which means that we could just like make it square because we have 2 lakes. If you're going to make it 3 lakes, it's going to be to the power 3. If you have 4 lakes, it's going to be to the power 4. So each lake dilutes and decay the signal by the factor of Q over Q of plus KV. 2 lakes in series apply this twice or squared. 3 lakes in a series apply this 3 times or to the power 3. Okay, now we come to a general cascade formula that if you have, let's say, a million lakes after each other, if you have a million CSTR after each other, you could apply the concentration at any CSTR, number of CSTR, or the concentration at any number of lakes in series after each other is equal Q over Q plus KV to the power number of lakes, number of CSTR, times the concentration original coming to lake number 1. Which means that each lake or each reactor in the cascade reduces the concentration by the factor Q over Q plus KV. So if there is an N lakes, the signal attenuation or the signal reduction is applied by N times. Of course, downstream, which is the farthest lake or the farthest reactor, concentration decay geometrically with an N, which is going to be to the power N. Okay. Let's look at, given the cascade, let me just give you the approaches that we might see. Hold on. So if you want to apply the generic model, we can solve this generic model using the same system, Q over Q plus KV to the power N times C original, C0. But if you want to plot it, let's see, if you want to plot it, ooh. Okay. Let's look at it like this. If you plot the x-axis as the space and the y-axis is the concentration, and you can see these are the reactors or the CSTR or the lakes in series. If you have one CSTR, the concentration is fixed throughout because it's only one CSTR. How about if you have two CSTR? The other one is one big CSTR, but now we're gonna divide it into two CSTR. So if you have two CSTR, the concentration initially goes from a higher concentration and then comes to the second CSTR and then goes back to a smaller concentration. If you have three CSTR, you would see that this different approach, that this concentration would be high, first CSTR, and then reduced to this to a lower value in the second CSTR, and reduced to a third value in the third CSTR. And it's really good that you should have more CSTR in series so you could reduce the concentration of the organic to a lower value. So how many CSTR in series you need? That depends on the value of the concentration of C value that you want to reduce it to. Sometimes you need 6 CSTR, sometimes you need 10 CSTR, depending on what will be the final concentration of C that you are looking for. Okay, so now let's look at the time variable general solution. Like when the loading is equal to 0. For one CSTR, let's just apply a single CSTR mass balance. VdC over dt is equal input minus flow rate times concentration minus decay times volume times concentration. When the loading is, stops, or there is no loading ends, this simplify to the following equation, that dC over dt equal minus lambda. Remember lambda we just had last time? Minus lambda concentration. And of course you could just go through it like that, and that will give you that lambda is equal Q over volume plus K, and this is for the first order decay. But when the general equation, and of course this has to be, when you mention that lambda 2,1, for example, it means this is the effect of a load into 1, okay, into 1 and concentration in 2, okay? So the load of 1, that's going to change the concentration in 2, and that is lambda 2,1. So if you also define some terminologies, and of course lambda 1,1, which is the lambda represent decay, flushing within each lake. Lambda 1,1 is equal Q12 over V1 plus K1, and lambda 2,2 is equal Q23 over V2 plus K2. And of course the feed forward coupling coefficient between lambda 1,1 and lambda 2,2, which is lambda 2,2,1, which can be approximated by Q12 over volume 2. This term represents the effect of concentration in lake number 1 on lake number 2. Okay, we'll show you that the dynamic equation for 2 lakes in series is by applying, if you have like 2 lakes, let's say we have 1 lake here, make it close, and this is 1 lake, the second lake here, this is lake number 2, and you'll have the let's say concentration 1, concentration 2, and you'll have Q12 that goes from lake number 1 to lake number 2. And if you want to do it, if you want to do the analysis for lake number 1, so dC1 over dt is equal minus lambda 1,1, which is the lambda of the first lake. And if you want to do the change of concentration with the second lake, it's lambda 2,1, which is coming lambda 2 affecting 2 from 1, okay? Lambda 2,1 C1 minus lambda 2,2, which is whatever happening inside the lake number 2, lambda 2,2 C2. The interpretation for all of this, that lake 1 decay independently, okay? You can see it. Lake 2 is forced or driven by lake 1, which is a feed-forward system, okay? And that is the lambda 2,1 C1 minus lambda 2,2 C2. And there is, of course, a change upstream, propagate downstream. Okay. And later on, let's just check the time variable that we might look at. Okay, and then this would give you the solution for the single lake. Remember the single lake from the previous lecture? This is the solution of the dc1 over dt is equal c1, c1 of lake number 1 equal c10 coming to the lake from initially, from previously, e to the power minus lambda 1 t. For the second lake, the effect will be different. And this is if you have a time variable solution. So the concentration leaving lake number 2 is equal lambda 2 times c10 over lambda 2 minus lambda 1 times the exponent plus c20 e to the power minus lambda 2 t. And if you do the same thing for the third lake, you're going to have this term. Now, of course, you could just go to the equation of 518, 521 in Chabra, and that's going to be by practice. I'll solve you an example in the next minute, and then you'll see how easy it is. Thank you.